Assalamu alaikum. Let's get started. Inshallah, today we will talk about several topics. Hopefully today we are going to finish whatever is needed to do the third assignment and maybe the final also. Next time, inshallah, I'm going to talk to you about the final, how it's going to be. So today we're going to, the first thing we're going to do is complete the code for classification. Basically, we had feature extraction. We had a code that has feature extraction and selection. Okay, we're going to continue on, and basically we did the features actually for the training set. We need to do that for the test set as well. So basically we're gonna do that, and we have to add the classification code. Last time we did that with the classification learner, but actually I'm going to show you how to do that with code. We'll just complete the code that we have already and have a complete program that does arrhythmia detection, and add the performance matrix at the end. So basically we're going to have the performance assessment at the end. So this is the first part we're going to do. The second part, we're going to look at the classification learner. Whatever we had last time, we have to look in some detail about some of the options that you have in the classification learner. And basically, we need to understand what they do exactly, so that whenever you use the classification learner, you actually get the best performance out of it. So we need to understand what's called cross-validation, which is one of the options that we had in the input. We need to understand what is called PCA, Principal Component Analysis. You probably heard about it if you attend the seminar, but actually I'm going to give you a very simple explanation of how it works and basically how you can utilize it to improve your performance. And we're going to kind of customize the way it does things in the classification learner. We're going to basically have a custom misclassification cost matrix. So basically, right now in the classification learner, it assumes that if you have an incorrect classification, whether if it was normal and you classify it as abnormal, or if it's abnormal and you classify it as normal, so basically both errors are the same. When we talked about the performance metrics, we actually emphasized that these two errors are not the same, because it's actually much more dangerous, much more harmful to have a patient with abnormality and you classify him as normal. Okay, so basically we need to adjust that in the classification learner so that we can get basically an optimized performance taking into account that. We need to understand the ROC curve, whatever we got there, the ROC curve. We need to understand what it means. And the last two things, actually, we need to link this classification learner into our code. How can we, or basically we need to know how to take the results from the classification learner and basically utilize them here to do the classification using the best models that we develop in the classification learner. Right now, you basically prepare the data and sit on the classification learner and get results. But basically, when you do that, you get just results, but you don't get a system. You cannot classify new cases based on whatever you got from the classification learner. You need to get the model that you developed with the classification learner and embed it in your code so that you can utilize it to get real results. So we'll basically know how to do that. When we do that, actually, we're going to compare the results that we get from the classification learner, which are based on cross-validation, to whatever we get on the test data, which are different from the cross-validation data. And basically, we will realize that we have two problems related to overfitting and underfitting. We're going to discuss these in brief. Okay? Do you have any questions? Okay. So I'm going to share the desktop now so that you can see Matlab. So basically what we had last time was this code. This is basically the code that develops the features, and at the end actually we combine the training and testing the training data actually and training labels so that you can get better results. Is this font enough, or should I make it a little bit bigger? Abdullah? Would you like to have it a little bit bigger? Should I make it a little bit bigger?
Yes, bigger is bigger.
Bigger? Okay. Is that better? Is that clear enough? More?
Yes, okay.
Is it clear, or should I increase it more?
If possible, more, okay.
Okay, this would be a little bit too big. Is that okay?
Yes, fine.
Okay. So basically, this is the code that we had last time. As you see here, we started with the learning data. And basically, we collected from the learning data, we collected the normal samples, which are the first 64 signals. Basically, this file actually has 256 by 1080. It has 4 different types of ECG, including normal and ventricular couplet, ventricular tachycardia, and ventricular bigemina. Okay. Basically, we have 64 signals from each one of these. So basically, I get the first 64 signals because they are the normal. We have to actually make it a classification between normal and something else. So basically, we choose the normal, or get the normal signals and put them in NSIG-learn, and basically choose which one of the other 3 types, the other 3 abnormalities that are present, and basically select it from there. And basically, we wanted, when I have 1 here, I get from 64 plus 1 to 64 plus 64. If I have it as 2, then I'm going to get it from 64 times 2, which is 128 plus 1, to basically 128 plus 64, and so on. So basically, we get the other type, or the abnormal type, by just setting this number right there. And basically, we had 2 variables here to accumulate the features. And basically, we got started, computing the features as we did before. And let me just run it for you. And at the end, we had the selection, the feature selection. So basically, we got, visualized the feature. And basically here, we ended up having 39 features. The useful ones, based on the t-test that we had, was 34 features. And basically, we selected these 34 and deleted the rest, and basically confirmed that by testing again, and we found that all of them are significant. So basically, this is where we stand. We have 34 features, and basically, we had 64 signals for the normal, 64 signals for the abnormal. We basically, at the end here, at the end of this code, what we did last time, we just combine the normal and abnormal for each, in one vector as a training vector, okay? Because these vectors, actually, this vector in particular was basically called from the classification learner, and basically we did the training based on it. In order for us to do that, we have to put labels. For each one of the signals here, we put labels. We had 64 normal, so basically we decided that the normal will have designed or designated as 1, and the abnormal will be designated as 2. So basically we had the labels here written for each one of them. So we have 64 1s and 64 2s. And these are the ones that we used for the classification, or basically for the classification learner to work, okay? The point is, we had another data set that was called, it's exactly the same name here. Instead of learn data 1, we had test data 1, okay? The test data 1, as we said at the beginning of this part of this course, we said that it has 32 samples for each one of the different types of ECG signals. So basically, it was designated as test data because we wanted to separate the learning data from the testing data, completely separate them. I don't want to use the testing data for anything but testing, okay? But the thing is, we have to realize that basically what we do now in the classification we basically moved from the data space or signal data space into the feature data space or feature space. Okay, this is actually, as we said before, if we have normals and abnormals, we have 128 signals times each one is 180 samples. Cases, sample. We ended up here with 128 times 34. These are the useful features, and this is still cases. Okay. Basically, if we use the signal data as we tried last time, actually it doesn't give us good results. So basically, it's much better to use features in order for us to do that. In order for us to do that, a more efficient classification and a higher performance of classification. Okay. The thing is, what we did, whenever we do that, we have to transfer both the training data or the training set and the testing set. Both. You have to transfer them to this domain. So basically, we have training features and testing features. We cannot do that for the training only. We cannot train, and basically for the testing we use the signal data. We cannot do that because basically we develop a classifier for the feature data. So basically I have to have the testing data in the feature domain or the feature space. So what we need to do now is basically we need to compute all features for testing data. Okay, so this is the first task we're going to do today. So we're going to go back to the code. The first thing we should do is basically load the testing data. Basically, we're just going to be following the original code that we had, but for testing data. So already there. Basically, if you look at the data, if you look at the data that we have here, basically we have test data 1 and test data 2, like what we have, like learn data 1 and learn data 2. For learn data 2 and test data 2, they were for the atrial fibrillation or ventricular fibrillation, which had a different sampling rate. This is the one that we started talking about actually when we talked about resampling. But actually right now we'll focus on the ones that are in test data 1, which are already 1080 samples for each signal. So basically we're just gonna use that. Okay, so here we're gonna basically do everything here exactly like this one here. Let me just copy this. It will actually have a smaller size. It's gonna be like 128 by 1080, and basically it has 128 signals, 32 signals for each. Usually it's a good size actually. You have the learning, basically when you do it this way, the testing data will be like 30% of the total. So if you have the total number of normal signals here will be 64 signals plus 32, 64 training and 32 testing. If you combine them together, they will be like whatever, it will be like 96 signals. We took 30% out of 4, or basically 1/3 of the data was for testing, and the 2/3 were for training. This is a good ratio. This is okay. Okay, so basically here we have test. I have to rename this file first so that we keep the original. We're gonna have it 10. Lecture 11, ECG, add 1, okay, because we're going to do computer-aided diagnosis now. We're going to add the classification. So right now, we already have the test data, and basically the test data variable is just like this one, but test instead of learn. So basically, I'm going to have. Basically, I'm just going to copy this and say nsig test is equal to test data 1. So basically it's exactly the same, but actually here is going to be from 1 to 32 only. And I'm going to do the same here because I want to follow exactly the code that I had for learning. So I'm going to have two variables like I had nSigLearn and aSigLearn, normal and abnormal signals for learning. I'm going to have nSigTest and aSigTest. So here also is going to be test data 1, and instead of the 64, because the size of the signals in the testing domain or the testing data is 32, so basically it's going to be exactly the same, but with 32. Now I have everything like basically the initial variables where I have the signals are there. I have to store the features also. The feature, feat N and feat A, were the accumulation, or basically the variables where I accumulate my features. So I'm going to have another set of variables. I'm just going to call them the same name and just add T. That's for testing. Okay? For each one of the features, what I'm going to do is just repeat whatever I had here. Sorry. Okay, but repeat it for the testing data. So basically, as you see here, basically I had these two for the learning data. I'm going to have another two variables for the same variables, but for testing data. And then when I combine, basically I'm going to combine now in the same variable with T, the new variables that I created. So basically this is going to be like this. And I'm going to add the two new variables that I have. Actually, this will be repeated in all the features. So basically I can just copy it now and replace all the other ones like it here. See here? So basically I just can copy the last two because the other ones are the same. So I'm just going to add these for all of them and then start correcting or modifying the features one by one. Have so many features, so basically I have to repeat that a lot of time. It's exactly the same, but it's kind of tedious work. So even for that one here, just add that. And then go back and continue changing the variables one. But I already did that here. This is the first feature. For a standard deviation, exactly the same way. I just copy these two. And basically have this feat 2, and instead of learn, I have tests. Just computing exactly the same features, but for the testing set. Okay? For each one of the features, basically no difference. Here, same thing. Unfortunately, there isn't a way to do that mechanically, like replace all or something like that. It's not like that. It cannot be done this way, so we have to do it manually. What I'm trying to do is to have all features calculated for the testing data like I did for the training data, so that when I use the testing data to try to see the performance of the model, I can do that. I can do that with the features from the testing data, because the model will only work with features. It's not going to work with the actual data, with the actual signals. This kind of tedious work, the worst thing that can happen is that when you finish replacing all these things, you find errors. Okay, so hopefully we will not have errors, but whenever we have errors, we have to go back and sometimes when you do things repeatedly like that, you usually end up with some errors somewhere, but hopefully not. Please let me know if you notice any errors. It's just a matter of repeating whatever I did for the training for the testing. I could have done that before the course, but actually I want you to see how it's done. Some things are not very exciting to see, but actually this is the way you do coding. I want you to know how to do that for yourself. So all I just do is just copy and replace learn by test. Median value. Getting close. This is the skewness, and this is the first. This is the fifth order moment. Just one feature to go. Yes, this one. That's it. So now here, basically, let's just run that first, just make sure that everything is okay. Okay, the error that we were expecting. Okay. Oh, okay. Here it should be feed. Okay, feed 2 n. Okay. Where is that? 2n. Okay, async test. I'm not sure why it's not. Let me check again. Feed 2n is 26 by 64, and feed nt okay, is feed nt 30 by 32. This is 64. 64 is different, of course. Let me check again. There's something wrong here. Let's see. 2n. Oh yes, there, right there. We should have, this is actually, if you remember for the Fourier transform, we computed the Fourier transform, and basically we were supposed to take only the first n over 2 points, but actually here I should have it from 2, feet 2n, not feet 1n. So this is the error. Okay, it worked. One very important thing after we do that, I'm not sure if you see the variables here, but here for the collection of features, we have feet 1, feet n, and feet a. Feet a is basically 34 by 64. 34 features by 64 cases. Okay. Feet at, which is the testing, is 39 by 32. 39 features by 32 cases. Why is that? Because basically for the features, the original feature, the training features, we did this part right there. Okay, we remove the features that are not useful. We have to actually repeat that for the feature that we computed from the test data, because we need to have the same number of features for both. So basically I need to do that here, and that's it. It should be, basically we are ready now to do classification, or basically use the testing data just like the other one. Now we have feet A, 34 times 64. Feet AT, the testing data for the abnormal, is 34 also times 32. 32 cases should be different. So now we have the X train and Y train that we created from the feature data, the feature that we computed. We need to have also X tests, test vector for the training data, testing data vector, and the labels for it. So basically here we're going to have feet NT and feet AT, the features that we computed for the test data. And here we have 32 cases for each, so basically this will be replaced by 32 here. Right now we have the data ready. We already collected the data, or the features, from the training and testing data sets. And we did a feature selection based on the training data. We cannot actually do that based on the testing data. We remove the features from the testing data based on what we found from the t-testing of the training data. So basically this is okay. This shouldn't be a problem. So basically the matter of selecting the features, it's okay. But we cannot use the testing data while we are selecting the features. We cannot do that. So after that, we should get started with the classification part. The classification part in Matlab, we can use these actually to go back and do the classification. Maybe I can do that again. And basically, I'm going to show you how to do that, how to get the data from there. But actually, let's just talk about it briefly. Basically, the classification in Matlab is done this way. You have the training data, and you basically enter it into a function, a fitting function, that will give you a model. This fitting function actually depends on which classifier that you want. So we have a fitting function for each one of the classifiers, or the families of classifiers that you saw in the classification learner. But once you have, so basically this is different for different classifiers. Once you have the model, that's it, okay? You basically have a function that is called predicts. Basically, it takes the testing data and the model, and gives you predictions, or gives you basically outputs. Let's just call them predictions. Okay, predictions meaning that for our case, for example, it would tell you if it's normal or abnormal for each one of the cases that you present to the prediction model. Okay, so basically you get this model, or this model basically is an input to this function, but this function is common for all classification methods. So basically this is a common function. So you use it for any model. So basically the way you're going to compute the outcome from the testing data is going to be exactly the same with the different model. Just put a different model into this particular function. Okay. So basically if you go back to Matlab here, if you go to the help and just look at classification. Okay. Okay, this one here. I just want to get the one that has the list of classifiers. These are the classifiers, if you remember, these are the classifiers we saw in the classification learner. Okay, each one of them actually you can get, basically you can learn how to use it from this here. So basically, if I just choose the nearest neighbor, basically you're going to have how to create a model. You're going to find a function called fit C, K, and N. Okay, how to predict, classify observations is predict. So basically we can just use that. Okay, let's open it in a new tab. It's very simple actually. It's just you put your training data here, and it's just look at it here. This is the X train and the Y train. That's it, and gives you the model right there. Okay. For the K and N, we need to classify, we need to specify the K, how many neighbors you're going to use. So basically there are options here where you can basically choose the number of neighbors. Let's just choose this one here. Let's just, let's just leave the standardized for now. I'm gonna copy this and put it here. Okay, that's it. Okay, here instead of X and Y, I'm going to put X train and Y train. Okay, and let's just leave the number of neighbors as 5, and then I want to compute the output. Okay, is there? I think it's probably here. It doesn't show how to predict. Okay, that's fine. You can see it probably from here. You can just see the help for predict. Here, see here, you just put the model and your X's for the training, for the testing, I'm sorry, okay? That's it. So basically it's very simple. Okay, so you feed the K and N, and then you predict after that. Okay, just predict this way, okay? So it's just get the label. Basically gives you the labels for whatever you have. So basically I'm just gonna say that labels, or I just call it, yes, predicted labels. Predicted Y, okay, or Y predicts is equal to predict with whatever I have here, MD1, which is my first model, and X test. That's it. Okay. Let's see what we get from here. Okay. We already have the data. Let's just run it. Okay. Okay. MD1 is not recognized. Maybe I should. Oh, it's MDL here. Okay. MDL, not 1. Okay. Model, for model. Okay, so it's finished. Already created the model right there with the parameters of the model. And basically now we have Y predicts, Y predictions, okay? Y predictions will be basically 1s and 2s like this, okay? 1s and 2s. How can we know how can we compare it to the true one, which is y-test? Y-test is the true labels for this. How can we do that? Basically, there is a very simple way to do that. If you put y-predict equal to y-test. Basically, this is not equal, this is not, this equals this. No, this is comparison, actually. You're comparing the two. When they are equal, you get a result, a logical result of 1. When they are not equal, you get a result of 0. Okay, so basically, okay, y predict, is it underscore? Underscore predict, okay. Yes. So now you have ones and zeros like this. How can you compute the percentage accuracy here? How can you do that? Actually, what you need to do is you sum all the ones and you divide by the total, right? Because basically it's going to be the percentage of the ones that were correct to the total number. But it's much easier actually if you use it like the mean. If you use the mean value. If you use the mean value, it's going to do exactly that because it's going to sum all of them and divide by the number. So now, right now, we have a mean value of 0.82. This is actually going to be 82% or 83% accurate. Okay, so basically here, after we do that, we say that the accuracy is equal to basically y predicts the same exact formula that we had, mean of y predicts equal to, or is it equal to y test. So basically, this is the first performance measure that we have. Basically, this is our model here. This is the classification part that we had. And as you see here, we just used any classifier. We did not optimize anything. And basically, we predicted the outcome based on this model. And then we computed the performance measure, the first performance measure, which is accuracy based on that. Right now, we need to compute something like sensitivity, for example. In order for us to do that, we have to compute something called a confusion matrix. Okay, how can we do that? Confusion matrix looks at whether y-test, the true outcome should be normal and it is abnormal, or the other way around. So basically, it doesn't make sense to do it manually. So there is a nice function in Matlab called confusion mat. Let's look at it. Very nice function. It does that for you. So basically, all you have to do for the confusion mat is just put the two groups. Basically, the group, the true value of the group, and the group hat. The group hat is the estimated values. So basically, if I did confusion mat of y test, comma, y predict. Okay, let's just do it right now. Here. It's going to give you something like this. This is basically, this is class 1, and you classify it as class 1. This is class 2, you classify it as class 2. This is basically class 1. This is class 2, you classify it as class 1. This is class 2. This is class 1, and you classify it as class 2. So basically, you got the confusion matrix right out of there right away. Okay, so basically, this is what you need. You remember, this is the true positive, this is the true negative, this is the false negative, this is the false positive. Okay, so basically, let's do that. Let's just define the 4 entries of the confusion matrix based on whatever we get from here. Let's just call this C1. Okay. So basically, true positive is class 1. Class 1 is negative actually for us. So basically, we need 2 and 2. So true positive is equal to C1 of 2 and 2. Because basically, it's class 2, and you classify it as class 2. True negative is C1 of 1 and 1. False positive, we need to have these as false positive and false negative. False positive means that it is 1 and you classify it as 2. The first one is the true one, and the second one is the predicted one. False negative, it is 2, but we classify it as 1. If you remember from the part that we talked about before, about the sensitivity and specificity and all these kinds of things, there's a table. Maybe I can bring it back. I think we probably talked about it in one of the lectures. Let me see. Here. Yes, here. Okay. Each one of these basically is just a definition, TP over TP plus Fn. Okay. You talk about the specificity is Tn over Tn plus Fp and so on. You basically you already have here in your code, you have TP, Tn, all the variables you need to compute any of these. So basically we're just gonna compute the sensitivity and specificity as examples, and basically you can use the other other formulas to do the other variables, the other measures. So the sensitivity is equal to true positive over true positive plus false negative. Let's just have it like this, maybe. Okay. Here the specificity is true negative. Maybe I can just leave it like this. True negative plus false positive. Okay. So when we do that, when we write like that, basically we're gonna get the accuracy, we're gonna get the confusion matrix, we're gonna get the sensitivity, we're gonna get the specificity. So basically we got the basically we have a complete program now. The one thing we didn't do is we didn't optimize the classifiers. So we need to know how to use the classification learner in order for us to improve whatever we have here. Okay, so basically what we need to do is to go back and run exactly what we ran last time, just try whatever we tried last time, and see how we can get the models that we trained and embed them in our code here. Okay, so basically what I need to do is, for the classification part, I would like to use something that would be actually optimized. But actually, what we're going to optimize is only this part here. Just the model fitting, that's it. The prediction is exactly the same. So I need to basically work with classification learner, which is, I'm going to start right now. Did you try a classification learner yourself on your computers or not? Did you have any problems using the classification learner app?
Let me check first.
Did you have any problem with the classification learner? Can you please close your mic if you're not going to speak? Yes. Okay, let's continue, and then we can talk at the end if you have any problems. We're going to create a session, and I'm going to use the data from the workspace. I'm going to choose X-train. I'm going to choose the response from workspace. It's going to be Y-train here. It's okay. The cross-validation, we're going to discuss the cross-validation in a second. We're just going to leave it this way. And we're going to start the session. Okay. What I'm going to do now is I'm going to try the, maybe I'll just try the all quick to run. Okay. The one that we used last time. Okay. Okay, starting the parallel pool takes a little bit of time at the beginning, just once. You can run without the parallel pool if you want to, but actually it's usually faster if you use the parallel pool. Okay. Okay, we got some good results here. We got, at least for the KNN, we got two models that were basically equal. Okay, this one and this one. Let's just consider this one here. This one here is, the model type is find KNN, number of neighbors is 1, Euclidean distance. There are actually some measurements here or some parameters here that we need to use for this function to work exactly the same way. So basically, either you look at the function that we looked at, basically the options of the fit CKNN, you will find these options. Basically, there are several options that you can use. Basically, this is a response variable name, okay? And basically, you have several options, basically these kinds of things, and you can specify them exactly as you saw here. This is a manual way of doing this. But we don't want to do it manually. We want to do it in a smarter way, okay? So the easiest way is just to generate codes, generate function. See here, generate function, okay? So basically what I do here, generate function, is going to give me a function that does the training. So this function actually contains basically the fit CKNN function that I want. This is exactly what I want, okay? So basically, the rest of the functions here does the cross-validation part, but actually the training itself is right there. So I can just copy it. I can just take the whole thing. Whatever, okay? And just basically copy it in my code. Where is my code? Right there. I can just have another model here. I can forget about the first one. I can now use this one here instead of classification KNN. I'm just going to call it model is equal to this. Okay. But actually here I have to replace this. The predictors will just be the X-train. Or maybe I can just use the same. If I'm going to do that a lot, I can just have these two here. Predictors is equal to X-train and response is equal to Y-train. Okay, that's it. Okay, so you should run it. See now, there's a difference now. The accuracy is a little bit higher than the one that we had before. Okay, if you remember the one that we had before, it was 0.82. Now we have 0.87, a little bit higher. The sensitivity here is also higher. The specificity is a little bit higher also. But if you notice, basically, this is the accuracy. If you look at the model here, the accuracy is 93.8%. Why is that? Why do you think there is a difference between what I got in my code and this one here? Can any of you answer? We hear from this code, from this classification app, we see that the accuracy of this model is 93.8%. What I got here was 87.5%. About 5% less. Why is that? Okay, this leads us to what's called how cross-validation does. What you have here is the validation accuracy. This is not the testing data accuracy. Usually when you do validation, you do something that is a little bit different from what you do with testing. Testing, you have completely independent data set. The data set that the model never saw. For the validation, actually, the data might be embedded, you know, that whatever you validate with might be embedded in the training somehow. So basically, it's a little bit different. the more reliable result is what you would get from the actual code if you try it on testing data. Okay, let's start with this first of all. Do you know how to get a model from the classification learner and embed it in your code now? Do you know that? Do you know how to do that or not? Let's try another one. Let's try another one that is not KNN. Let's try tree. Okay, tree model is about 89%. It's not the best one, but we actually can use it and try it. So we go to generate function. This is for the tree one. Now what you're gonna see here is another function that is fit C tree. Basically here it's fit C with the model here, and if you do the SVM support vector machines, they're gonna be fit C SVM. Okay, so basically I'm just gonna get this code right there, and I'll use it there in my codes. So basically, I'm just gonna comment this out. This is one of the things that I tried. This is the one that we tried before. And basically, I'm just gonna say this model equal to this. That's it. I got the results from the model from the tree right there. And basically, as you see here, it's very simple. Just change the function and you get basically a different classifier family. Let's try it. Now the accuracy is still 87.5%. Okay, is that okay? Yes, it should be okay. Yes. The sensitivity, is it exactly the same? 96, 7. It's exactly the same. So I'm kind of worried that we might be working with a different model. Let's see. Let's just clear all at the beginning so that we make sure that we don't use an earlier model. Actually, it's exactly okay. MD1. Okay, so we had an error. So it's MDL also. MDL, not MD1. Right? MDL. So this was line 321 right there. It should be okay. Oh, okay, sorry. Yes. And capital. Very small errors. Okay, now it's a little bit different. Now it's 85, about 86%. The sensitivity is a little bit lower, but the specificity is a little bit higher. Okay, so basically this is the way to get whatever we want from here. We optimize here and get the optimized model and just implement it in basically one of my codes in order for me to get the exact performance, or basically the best performance I can get. So basically here, just consider these numbers as estimates, and usually it's overestimated. You know, the overestimate, or basically it has what's called overfitting problem. So basically whatever you get from here, from the validation, will be a little bit higher than what you would get from an independent testing data, or basically the testing data considered as the actual operation of your classifier in the field. So basically whenever I do testing with completely independent data, I get some real results. I get some practical feedback that would be exactly the same as the one I would get from the actual deployment of this classifier in the field. Okay, so consider these numbers, not exact, but basically the relative values of these is important. So basically if I get an accuracy here of 93.8%, this would be better than the one that had 53.1%. Okay, so this means that this classifier is definitely better than this one. They will never be this high from the point of view of accuracy, but actually relatively they have the same they are reference to the same thing. So basically, you should optimize here and get the best model from here, and then use it on your practical data or your test data to get what this model would do in practice. Okay? Is that clear? There's an alternative of doing that. Instead of having a function or retraining everything again, you can actually export the actual model. So basically, I can say here, export model. Okay, when you export the model, it will export it as basically, instead of training to get the model, it will give you the model right away. So basically, let's just you can call it here whatever you want. So it's train model what? Train model 1. I just put 1 here to have a different name. When you do that, basically it tells you if you want to use this train model, you do it this way to do the prediction. Okay, it has a little bit different way of doing the prediction. It's basically it's a structure, and it has a function called predict function here with it, so that you can use it right away. So basically, I can do exactly what I did before, the y predict. Not sure where it went. Y predict or y fit. Maybe I can just take the y fit the way it is right now. So basically, I just copy this and put it here. And instead of x, I put x test. Okay, and it would give me the predictions based on this model. If I wanted to keep this model, I can save it as a .mat file if you want to. You just say save and file name and put this model so that you can use it later on. It's the variable here. If you look here, the train model is right there. Okay, it's a structure, it's a data structure that has the model and the functions to use to predict as well. So basically, if I do that, I can also do the whatever I did before, basically. So I use now y fit and just get the accuracy right away. So I can either save the model or I can save the training function. Okay, sometimes it's better to save the training function so that you would remember the parameters that you use for this function. Okay, so basically, as you see here, for the model, for the function here, you have all the parameters of the function. Whatever you change here, basically, whatever you choose, the optimal parameters or the kind of selections for these parameters will be there already. If you go here and basically remember from last time we had, we can optimize. So for example, if I got optimizable tree, for example, okay, or optimizable discriminant, and all these are different families, by the way. When I ask you to do classification using different families, these are the families: decision trees, discriminant analysis, logistic regression, naive Bayes, support vector machines, and so on and so forth. Okay, so basically, if I choose discriminant analysis, for example, and use this optimizable discriminant analysis, so basically this will actually go through the different options in this classifier and basically optimize these features so that I can get the best possible combination of options for this classifier so that you can use it to get the best possible results. So basically now it's optimizing that. See, now it's changing the parameters. Basically the parameters that you use are called hyperparameters. Okay, so basically if I choose, for example, here, for example, for this particular one, I think the discriminant, you have linear classification, linear discriminant analysis, or quadratic, or diagonal linear, or diagonal quadratic. You have different options. And basically, it goes through all these options, any options that you may have, and basically sees which one is best and chooses that one and give it to you. Okay, so now basically it has only one step left. That's it. Okay, so now we have 92% for the optimizable discriminant analysis. If I go here and generate the function, basically you're gonna get the training function here, as you see, with the optimal features that you got from that optimization. Okay, so basically this will help you if you want to optimize the KNN, for example. You can optimize the KNN. It optimizes the number of neighbors, optimizes the distance measured, optimizes all kinds of options that you have in the KNN. And basically, what you will get from the training function is basically that last set or that optimal set that will give you the highest possible performance. Okay, is that clear?
Yes, sir.
Okay. Okay. So now let's get into the classification. We have here, as we said before, when we have the new session, okay, we have here something called validation, cross-validation that you choose, okay? I choose here X-train. And this here from the workspace, basically X-train, because actually there are several ones with the same. Basically, it chooses the response with the dimension that it expects. If you have here 128 times 34, it looks for a vector of 128 times 1. So if you have multiple vectors with this dimensions, basically gives it to you here as options. So basically, I'll just use Y-train. And here I have cross-validation, and basically the cross-validation, you specify what's called number of folds. Number of folds, okay? What does that mean? We need to understand that before we use it, or basically, or at least understand what it does so that we understand the results from it. Basically, this is a very interesting option when you have small data set. Okay, so basically this is a very good option. Okay, so basically if you have like what we have 64 cases for normal and 64 cases for abnormal. Okay, usually it's better if you divide your data into independent training and testing sets. If you do that, here you have 128 total, right? If you divide these 50-50, here you have 64 only here and 64 only here, right? Just only very small numbers, okay? And this is a big problem because you usually need a lot of data to do good training. So the cross-validation, if you have 5-fold cross-validation, what it does is basically you take 80% for training and 20% for testing. But this is a problem because the 20% for testing is not good because it's a few testing samples. If you lose one of these, each one of the testing samples that would be classified or misclassified, it would basically lose 5% of their performance, basically. If you have 19 out of 20, it's 95%. If you have 2 out of 20 incorrect, it's 90%. So basically, you're moving with very coarse steps, okay? So basically, this is not a good thing. But actually, when you do that 5-fold, you repeat that, not just do divide like that, you repeat it 5 times. Meaning that I would take, if I have a data set, for example, if I have the data like this, just consider the data as basically this here. Okay, these are 80%, and the testing would be this, the first iteration. The second iteration will be like this. The third, let me draw them all, and then So basically, the red is the testing. Red is the testing, and blue is the training. Okay, and you do that basically. This is the first fold, this is the second fold, this is the third fold, this is the fourth fold, and this is the fifth fold. Each time you train with 80% and test with 20%. At the end, what should I do? How can I combine the results from all these experiments or from all these folds? How can I do? Basically, each one of them will give me the results, right? What should I do with the results from all these? These are definitely different. Each time I train differently. So basically, each time I consider that I don't have anything, I don't have any background. I basically just divide the data in a different way. Okay? And basically get the results from each one of these. If I do that, I should average all of them and consider the average as an estimate of the validation. Okay, so this way I have good training sets, basically large training set, and still have good accuracy, good testing accuracy. Okay, so this is what I'm doing in my cross-validation. Okay, so each time I train, and basically each time I repeat the training 5 times if I have 5-fold cross-validation, and basically repeat that and basically compute the average at the end. The point is, when you're doing validation, you're using the data. This is the con or the drawback of this. You're using the data, the validation data. Let me write it validation because it's important to write it. But actually, this is actually called now validation. You use validation data to optimize the model. Meaning that you choose classification or classifier model that gives the best validation results. Optimal validation results. And this is actually a bias. You're biasing your model because basically, if you're, for example, I just want to try and give you a good example. Now you're choosing the model based on whatever gives you the best performance on this particular data set. Okay, and this is not a good thing. Because basically the data out there, the practical data might be a little bit different from it. So you optimize the model based on validation, and then you have to, in order to assess true performance, you have to use independent testing data. Okay, so basically the validation data that you use, or basically the validation that you do, basically helps you to optimize the classifier. But basically, sometimes the data are different. Basically, you might have insufficient validation data. You have very small number of cases, for example. Okay, this very small number of cases might exhibit some very peculiar characteristics that may not be in the general population. So if you depend on it to optimize your model, okay, it will give you very good results on the validation data. But unfortunately, when you go and look at other data points in the testing data, you might actually get something different. So basically, this is very useful. You can get very good results out of it, but actually, you have to make sure that when you try it on the testing data, that the results are still okay. Okay? This is a very important matter. Okay? So this is the first point that we have to take into consideration. Okay? I have a suggestion because I hear Maghrib prayer is now. Would you like to take 15-minute break so that we pray Maghrib and come back at 6:05, for example?
How much time we need, Dr.
I think we need, let me see in the lists. We need 30 minutes. We're probably going to be done by 6:30 anyway. But 6:30 is too late for Maghrib. So basically, we need to understand PCA. This misclassification cost, actually, you can do it right now. We don't have to wait. This is not going to take that much time. Actually, it's probably going to take about 15 minutes, not more than that. 15 minutes, 1-5.
Okay, we can.
Would you like to continue and finish?
Can we continue to one time?
Yeah, sure, no problem, no problem. Okay. So basically, this is the cross-validation issue, okay? So basically, validation is done this way in the classification learner. You actually, when you open the data, when you choose the data, or when you try to get your data, basically, you choose a number of cross-validations, and actually the performance might change with the cross-validation. There's a difference between cross-validation and holdout validation. Cross-validation works the way I told you about, okay? You have number of folds, and basically you keep changing. If you have 5 folds, then you divide your data into 5 sets and choose each time, you choose 4 of them and test with the other one, with the last one. There is holdout validation. Holdout validation does that once. So if I choose that, it's basically going to take 25% of your data. For example, if you choose here 25% and separate it from the other ones, it's just going to do it like a one-fold validation here. So basically, it's going to be like what we saw here. It's going to be only like one of these. Okay, it's just going to do that once and that's it. It's not going to do cross-validation. Sometimes when you do that, it gives you results that are closer to practical values, but actually it's not a good idea to do that with very small data sets like the ones we have. So it's better to choose the cross-validation. Okay? So this is important. So if you go back here, so do you understand now what cross-validation is? So you can change the cross-validation parameter, how many folds you're going to use, and you can try that and compare it to the holdout validation and see basically whether the model is better this way or that way. These are options for you to try and basically get some experience on what each one does. One very important thing here is that, as I told you before, we have a parameter here called misclassification costs. As I told you before, there is a difference for us, you know, between the errors here, the error here, and the error here. Here basically gives you the classification error. When it does optimization, it computes the error. And for each one, if you basically have a true class of 1, and predicted class of 1, the error is 0. So basically you have cost of 0. And also the same for 2 and 2. But here you have 2 and 1, and 1 and 2 you have different parameters. This is the true class, and this is the predicted class. So if I wanted to have a different weight for each one of these, okay? So for example, I want to have a less weight for the, when I have a true class of 1, and a predicted class of 2. So basically, I can come here and choose that or put that as 0.5. Okay. If I do that, basically, I change my basic misclassification cost. If I go back here to the classification learner, to the same exact one that I was working with, after I do that, basically, if I said OK on that, okay, then I can go back here for this one and start again to train. It might give you actually some good results, some better results. It's definitely going to be different. Okay, I'm going to show you how now. Now it's trying to learn, basically. Probably for the discriminant analysis, actually the options are not that many, but if you actually work with KNN or something like SVM, you're going to get much clearer results. The main difference will be basically in the ROC curve, or the confusion matrix, I'm sorry, okay? The confusion matrix will be a little bit different if you do it this way. Let me show it to you. Actually, the number of 30 years is a little bit, it takes a long time, because usually it's, you're not going to get much improvement, actually. It's exactly the same, because basically it's, the classifier itself is not really that, really that useful, but I can get that. Let me see the ROC curve first. The ROC, not the ROC curve, I need to use the confusion matrix. Confusion matrix here you have 2 and 1, you have 7, and here you have 3. Let's see the other model. If you click on the other model here and look at the other ROC curve, it's actually almost the same, so it didn't change that much. Let me try one for the KNN, for example. But in order for the KNN to finish quickly, I'm going to have to optimize the advanced features here. Here, basically, you decide the way the classification or the optimization is done. So basically, instead of optimizing the number of neighbors, I'm just going to keep the number of neighbors as 1. Okay, so that it basically shortens the amount of time that I'm going to take for the classification. Or for the training. So here, I'm going to keep that here, and I'm going to train it now. If you use it this way, it's going to try to make the error, you know, the part of the error where you have a true class of abnormal and a predicted class of normal to be minimum. So even though the accuracy might be the same, but actually it's going to shuffle or basically change the model so that most of the errors happen in the other way, in the case where the actual case was normal and it was classified as abnormal. Maybe I should change the number of iterations also so that doesn't. Okay. So it's 93.8%. Let's look at the confusion matrix now. Now it has 5 here and 3 here. Okay, the true class here is 2 and classified as 1, so it's 5 and 3. Let's try the same exact model with the classification costs back to 1 and 1. Okay. So basically, this can be used to optimize your model so that you avoid that very harmful case of having a patient with abnormal arrhythmia and basically give him a classification of normal. So now it's 94.5%. Let's see the confusion matrix. Now it has 5 here, 5 and 2. Let's look at the other one. It was 5 and 3. It actually didn't change that, but this one actually became less. So basically it optimized this one here, but actually in other cases you might see that this one became a little bit lower, because basically this is the case that you had a very high weight for. Let me try it again with a higher weight. Put the misclassification cost here as 5. Okay, so this is 1 and this is 5. And let us just use a little bit less iterations here, maybe 10 iterations, so that we can finish quickly. So now it's 94.5%. Let's see the confusion matrix now. It's exactly the same. Okay, maybe this is not a good model. Maybe we should look at the different K here. But usually when you put a classification cost for one of these as higher, you should actually see a decrease in that part. Okay. Sometimes when you use a very limited options, if I use here K is equal to 5, for example, maybe it will give me some better optimization. Let's see. It's 88. It's not very good. Let's see the confusion matrix. Now see now the difference. Now it had a lot of errors here, but the error that I'm afraid of became almost not there. So basically, it now gave me a much better result for this one here. If you use optimization for the K as well, you might get very good results like this kind of percentage or even higher. But actually, you will keep that as low as possible. So this is one of the important things that you need to look at in the optimization, how to put misclassification costs to get better results. The last thing we need to talk about today is principal component analysis. If you attended, there was a lecture about blind source separation. Basically, this is one of the tools for blind source separation, basically. The principal component analysis is a way of summarizing features. Okay, so principal component analysis, or PCA. Basically, it takes features. Basically, as order we have, for example, 128 times 34. Okay, these are the number of features. So this means that we have a space of 34 dimensions. Okay, 34 dimensional space. This is not a good thing. If you're trying to classify with a very high dimensionality like this, you're probably going to end up complaining about the amount of data you have. If you can reduce this to, for example, 3 or 4D, that would be much better. This can be done naturally with principal component analysis. Let me give you a 2-dimensional example because I cannot give you a 34-dimensional example. Okay, let's just consider data that look like this. If I have 2-dimensional data. Okay, and basically your data points look like this. Basically, if you look at the data itself, you can actually fit whatever you have into an ellipse. You have an ellipse that basically surrounds the data like this. Should write it a little bit better. You have an ellipse. Basically, you have two dimensions. You have one dimension here that is much larger, and another dimension here that is much smaller. Okay, if you have your data like this, then it's better to rotate your axes to have axes looking like this. If you do that, then you actually can neglect that, because actually it doesn't really contribute that much. Most of the variations or variance of the data is in one dimension. This actually takes into account the dependence of the features. So basically, if you have 34 features, sometimes many of these features represent exactly the same thing, or very closely the same thing. We represent exactly 90% of whatever you have. Okay, so basically the PCA, if you have 34D space, you enter to the PCA, and the PCA will give you the one that has the highest variance, and the second, and so on to the lowest, and gives you exactly the percentage of energy or the percentage of the original data, the percentage of energy present in the original data that is represented by each one of these. So it gives you directions of highest variance. So you can either select basically number of directions to keep a certain amount of energy, or you can say that I'm going to take 4, and that's it, whatever the percentage of energy will be. Okay, this can be very useful in making the training much more efficient. Let's try that. If I say here, if I click, just we go to PCA here and just click this one here, and here you say explain, specify the explain variance 95%. Then you selected whatever number of directions that keeps 95% of the energy present. You just ignore. Basically, if you consider this example, when I neglect this direction and take the values in this direction only, I remove the part of there is an error because I neglected that part. Okay, but if this represents 95% of the energy, then basically I might not need the other one. Okay, so basically it selects here the number of PCAs, number of principal components that keep the 95%. Or I can specify the number, can say that I have only, I can choose myself, for example, 5, and that's it. Let's try the one with the 95%. This is much more practical, and basically 95% is a really good approximation to your data. When I do that, basically, for example, I can choose one of the, I can probably choose the quick one. Basically, here in the current model, you're going to see that PCA is enabled, and basically tells you exactly, the direction that it used. Basically, the first one only, it had almost 56% of the energy. The second one, 36%. The third one is 30.7%, and so on. As you see here, it gets much smaller, after that. Okay, so basically, if you do that, basically, if you want to have 95% only, then you can keep only 3 of them, the first 3. As you see here, these first 3 are almost You know, they are much more than enough. You can probably add the fourth one if you want to, but this is actually is very good. The thing is, if you look at the results here, sometimes you find that the results are better, sometimes you see that the results are worse. So basically you have to look at this, you have to look at this option. But whenever you get good results with this, it means that your data might have basically some noise, and you remove that noise by doing this. Let me try the other way around here. I'm just going to specify the number of components. Here I'm going to use, for example, 5. Let's just keep the 5 here. And try the same thing here. Actually, I chose only the fine tree. I should have a quick hold. Actually, the results here are better than with the other one, with the 95%. So basically, sometimes you might want to do it and try it if you see things that might actually not be as good. So this is one of the options, but basically you have to try it and see if it works or not. If you have so many features, depends on your features definitely. If you have so many features and they are related to each other, then it's very good to use PCA. If the features are not related to each other, then the PCA might actually basically lose some information that might be useful. Okay, so you might want to try it as an option. But basically keep in mind that PCA is a way of summarizing your data. So when I say that, if I keep only 5 components, then the problem now became basically I have 5 features only after the PCA. I basically take the combined features that the PCA provided for me and use them instead of the original features. And these combined features will be basically made up of all the features, all the dimensions. Like my example here, these points here basically have X and Y. If this is feature 1 and this is feature 2, but when I have them here, they are like one feature. But each one of them came from these original 2 features with different weights. So this is exactly what I get from PCA. So basically, this is one of the options that I would like you to try and basically utilize if it's useful. Okay, so when you optimize with PCA and see what you get, and you optimize without PCA and see what you get, and that's it. Do you have any questions? So now we covered all the other parts, all the parts that we talked about. Basically, the remaining 2 parts, ROC curve, probably I'm going to talk about next time. It's just a matter of, maybe you can just talk about next time with the overfitting and underfitting, okay? Next time, inshallah, I'm not going to cover any more material. What I'm going to do is to answer your questions and explain to you the assignment 3. If you have any problems with assignment 3, I'm going to go over it at least and tell you exactly what I want you to do. And I'm going to also post the final exam, and it's going to be take-home exam, just like the assignments. And I'm going to explain it to you, inshallah, next time. Okay?
Okay.
Do you have any questions? You have any questions?
Thank you very much.
Okay. So if you don't have any questions, then inshallah we'll meet next time. If you have any questions from now till next time, please feel free to contact me or send me an email or whatever, okay? Next time, inshallah, is going to be the last lecture, inshallah. Okay, the last lecture doesn't mean that if you want to contact me or meet me to ask me any questions, I'll be happy to do that, okay? After the last, but this is the last formal lecture, inshallah, next Friday, okay? As per the university regulation, actually, the university mandated that. Okay?
Okay.
Okay, doctor.
I'll see you next time, inshallah. Assalamu alaikum.
Wa alaikum salam.
Wa alaikum